In our last class, we talked about one-way ANOVA. We treated t-test for one sample, t-test for two samples. We'll discuss one-way ANOVA. We are going to continue from there. So today we're going to treat two-way ANOVA. Then for two-way ANOVA, we'll talk about two-way ANOVA with replication and also two-way ANOVA without replication. So let's see how far we can go today. So we know when to end the class. Okay, so let's start. Like I explained earlier, one-way ANOVA has one factor. It has one factor and replication. If you are talking about, let's say I want to compare, and take note of ANOVA. ANOVA, you have more than two groups. So you have three groups or more. When you have two groups, it's better use t-test. If you have one group, t-test. When you have more than two groups, use ANOVA. If you have only one factor and replication, use one-way ANOVA. For example, if you're talking about, you want to compare the CGPA of three departments in photo, let's say statistics, mathematics, geology. In that case, you can use one-way ANOVA. We have three groups, and the factor there is the different departments. So we have three groups. The factor there is the department, and this department has three levels. So factor is department, three levels. So because we have only one factor, one-way ANOVA. Now, assuming we decided to group it. Let's want to have two factors, and the second factor will be the block. Want to group it. Let me explain what I mean. Now, if you don't group it, if you don't block it, you can be comparing a student from year one in mathematics with another student from final year in statistics. Now, if you compare that, you know that they are not on the same page for you to compare them. So a student from final year has up to 10 semesters result. So he's talking about the cumulative result of 10 semesters, while students from year one, just 2 semesters, maybe first and second semester. So it's not proper to compare both. So you can decide now to create a block to group them. Yeah, you compare all the year ones from all the departments, all the year twos from all the departments, all the year threes from all the departments, to all the year five from all the departments. Now, if you try to introduce blocking, now we call that randomized complete block design, RCBD. So that's two-way ANOVA. Like I said, we have two-way ANOVA with replication, with interaction, and two-way ANOVA without interaction. So two-way ANOVA. So let's start with two-way ANOVA without interaction. We're going to use the example of bulbs. So we have three companies producing bulbs. So that's the example we're going to use here. So let me copy it. So before this class, I was able to create, in our last class, we did this three. So before I started this class, I was able to create another variable called group so that I can use it for two-way ANOVA. So this is my blockings. I want to block them. So let me change it to block. Let me block. So I want to block them. So let me show you how the data is. I've explained why I'm setting seed, because I'm simulating data. So I have to set seed, meaning I want to select the box that I want to simulate my data from. So I can choose any number. 40 is not fixed. You can use any number. So I can try to use 25 or 26. So you set seed. Now, the reason why you are setting seed is so that whenever you simulate, you get the same result. Now, if I don't set seed and I simulate, I will not get the same result. I mean, if I run the analysis, so look at what I mean. If I run the analysis, I can arrow unif. I can simulate two data, 0, 100. So this is what I got, 68 and 87. Now, if I run it the second time, look at what I got. I see I didn't get the same result. If I run it again, I won't get the same result. So that's the essence of setting seed. But let's say, assuming I set seed before simulating my data, I can choose any number. So I can choose 1000. So assuming I set seed, look at the result I got, 32. if I repeat the same analysis, I will still get the same result. Are you seeing it? So that's the essence of setting seed. So why do you set seed? You set seed so that whenever you simulate data, you get the same result. So now you can use any number. That number there just means the box you want to simulate from. Just see it as a box you are collecting your data from. So whenever you go to that same number, you get the same result. So I'm simulating data from uniform distribution for the first company, alpha box, uniform distribution for the second company, beta box, uniform distribution from the third company, gamma box. Now let's assume that these three companies, they have three types of bulbs they produce. Let's say they have three types of bulbs they produce. So the first type is, let me call it energy bulbs. So let me call it energy. The second one, what would I call it? I don't know names of bulbs, so I can just call anything. Let me just call it light bulbs. Then the third types of bulbs they have is, let's say, high bulbs, or let me call it expensive bulbs. Then the second one, let me call the second one cheap energy bulbs, cheap bulbs, and expensive bulbs. So what we are trying to do is, now these three companies, they produce bulbs. So now let's compare all the bulbs, all the energy bulbs from the three groups. Then we also compare all the cheap bulbs from the three groups, and we'll compare all the expensive bulbs in the three groups. Rather than just comparing or taking all the bulbs and comparing them together. If you take all the bulbs and compare together, it's possible that you'll be comparing a cheap bulb and an expensive bulb from different companies. And when you do that, the results may not be accurate because the difference will be significant because you are comparing bulbs of different quality and of different nature. So that's why it's good sometimes to block if it is possible. So blocking will help to reduce heterogeneity and improve homogeneity. So meaning the variables, the subjects within each block will be homogeneous and to reduce variation among them. So that's why we're trying to block. So let me show you the data now. So we block. So we have a data frame. I brought all of them together. So I believe we should know this. We did this in our last class. So this is the data. No, this block. Let me change this to block. Block. So let me run bubble. Correct. So this is it. So energy bulb produced by alpha is 86, 65, 197. The second type of nature of bulb, cheap bulb, 78. We're talking about their lifespan. The expensive, 74, 89, 95. So that means if we want to compare, we'll compare energy bulbs from the three companies. We'll compare cheap bulb from the three companies. So that's what we are going to do. Rather than comparing everything without considering the nature of the bulbs. So now looking at this, now we have two-way ANOVA. What are the two factors? First is the block, and the block here is talking about what the nature of the bulbs, and the second is the different companies. So we have bulbs, the nature of the bulbs, and the companies. So these are two factors. So because we have two factors, we are going to use two-way ANOVA. Now, first, we are considering two-way ANOVA without interaction. Now, this is two-way ANOVA with replication. Two different things. Replication. Why is it replication? Look at this. Energy is there. We also have another energy here. So it means energy has been replicated 2 times. Another energy here 3 times. Another energy here 4 times. So this is two-way ANOVA with replication. Take note. Why is it two-way ANOVA with replication? Because the subjects are replicated for the combination of each factor. So if you compare energy, you see that it's replicated. So this, assuming we have only this, let me just show you only this, what I just highlighted. And this is the only numbers we have for the analysis. We call it two-way ANOVA without replication because energy is not replicated. We only have one value for energy and alpha bulb. We only have one value for energy and beta bulbs, and also have only one value for energy and gamma bulbs. So assuming this what we have is two-way ANOVA without replication. But because we have another variable for energy under alpha bulb, another variable for energy under beta bulb. So and we have another variable again for energy alpha bulb. So we call it two-way ANOVA with replication. Take note. Now, what we are solving now is two-way ANOVA without interaction. I will explain what I mean by interaction. What I just explained now is replication. So I believe everyone should have understood what I mean by two-way ANOVA with and without replication. I will explain interaction later when we get there. Now, if you want to do two-way ANOVA, Aru doesn't understand. You have to arrange your data the way Aru will understand. Aru doesn't understand the data if it is arranged this way. Now, how do you arrange your data? You have to arrange your data so that all the numbers will be in one column. All the numbers, all will be in one column. That's what Aru understands. Aru doesn't understand this. Now, how will you do that? This is the data currently is arranged in the wide format. So I have to change it to the long format, which I've taught earlier. So I have to change data in the long format. Now, before you do that, remember you have to call up our library, TIDYR. You call up the library. Then you have to gather your data. So let me call it set1. So set1. So the code, let's convert it to long format. We use the code gather. Then you type your data. What's the data? Our data here is box1. The next thing is the key. What do you want to call your key? The key is different companies. So our key here is different companies. Then the next thing is the value. What's the value? Our value here is, the value represents lifespan. So the value here represents lifespan. Now, the next you have to tell Aru what and what Aru should gather together. I don't want to gather the block. So the numbers I'm gathering is from alpha bulbs. So I'll write it alpha bulbs. Then I will use my colon. Alpha bulbs to what? Gamma bulbs. So what am I telling? I'm communicating to Aru. Don't touch block. Don't gather block together. Only gather alpha bulbs to gamma bulbs. So I can run this. Now let me see how my data is. So I will write the name of the variable. Or another way to do it is to put a bracket here. You put a bracket here and end it with another bracket. So when you do this, you are both, which I've explained earlier, you are both assigning a new variable set1, and also you are telling Aru, assign the variable and show me what is there. So look at it. So this is how to arrange your data if you want to do two-way ANOVA. Two-way ANOVA. This is how to arrange your data. Now, how do you arrange your data so that all the numbers will be in one column, one column, one column? Now look at the two factors we have. The first factor we have is what? The block. The second factor we have is what? The companies. So we have three companies here: alpha bulbs, beta bulbs, gamma bulbs. Then we have the nature of the bulbs that they produce. The cheap bulbs, expensive bulbs, energy bulbs. So we can compare now. Very simple. So what I skipped, I've been trying my best not to go too deep into statistics. I want to explain something, because if you want to be a data analyst, you have to do that. Before you can do a parametric analysis. Now in statistics, we have parametric statistics and non-parametric statistics. Now parametric statistics have a lot of assumptions, a lot of conditions that the data must satisfy before you can use that particular method. Why non-parametric may have little or no assumption, little or no conditions that the data must satisfy before you can use the method. Now, for one-way ANOVA, there are conditions that must be satisfied. If these conditions are not satisfied and you use that method, you will get inaccurate results. Okay, let me use for an example, regression. Regression has different assumptions. We have the multicollinearity assumption, we have the autocorrelation assumption, we have the homoscedasticity assumption, we have the linearity assumption, we have the outlier assumption. So all these assumptions must be satisfied. Now, once your data fail one of these assumptions, you can't continue. Just like the WAEC we write in Nigeria. If you pass all the subjects and fail mathematics, you can't proceed. So the data must satisfy all the assumptions. Now, Because if they violate any of these assumptions, it will affect the accuracy of the result, and any conclusion drawn from that analysis may not be accurate. In our first class, when we treated one-way ANOVA, I tried to avoid saying all these things. But I think it's necessary, because if they give you a work to do, an analysis to do, the first thing you have to do is to test for the assumption, to check if the data is suitable. Because if the data is not suitable, you don't have to continue. Now, just see it, if you're in Nigeria, just see it the way we do post-UTME and JAMB. If you don't pass your JAMB, you can't write post-UTME. So if you don't pass the assumption, you can't do the analysis. Now, let's talk about two assumptions. Let's test for the assumptions before we do the two-way ANOVA analysis. So let's test for normality. We're going to test for normality assumption. What's normality assumption? Well, normality assumption states that the errors of the two-way ANOVA or one-way ANOVA, depending on what you are dealing with, follows a normal distribution. That's what it is. So if they discover that the errors do not follow a normal distribution, it means any analysis drawn, any conclusion drawn from that analysis will not be accurate. The second assumption we are going to talk about is constant variance. Another name for that constant variance is homogeneity of variance. Another name for homogeneity of variance is homoscedasticity. What is it saying? Is that the variance of the error term is constant. The variance of the error term is constant. Whenever the variance of the error term is not constant, any conclusion drawn from the results will not be accurate. So let's test for that. In our last class, I talked about the Levein test, which we did. I said we use the Levein test to know whether we are to assume equal variance or not. So we are going to use the Levein test now. So first, what do? First of all, you have to set up your model. You have to set up your model. So let me call it model. Let me call it model 1. How do you set up your model? You assume we are doing the two-way ANOVA now. While I'm doing it, I'll test the assumption. So for you to do the two-way ANOVA, you have to write a linear regression model for it first. That's the code. So let me make my comment. I'm doing a what? Two-way ANOVA without interaction. Remember, we're talking about two-way ANOVA with replication and without interaction. Okay, so I said we'll create a linear model first. Now, whenever I want to do a linear model, you do LM. So I should have taught regression before doing ANOVA. Well, let's continue. LM. So this is how to do regression. Well, first of all, for you to do two ANOVA, you have to, with arrow, you have to write a linear model first. Then what will come first will be the name of the variable that contains the values. So the name of the variable that contains the values there is lifespan. So I will write my lifespan. Arrow is case sensitive, so you must use arrow is case sensitive. You must use the case the same case, similar case that is there. So lifespan. Then use this symbol. Then you write your factor. So the first factor is the companies. Remember, it's case sensitive, uppercase C. Then plus the second factor. Second factor here is block, and block is lowercase c, comma. Then you write your data. So my data is equal to what? What is the name of the data I'm using for this analysis? Set 1. I can run my analysis. Company is not found. Yes, because I didn't spell it well. Correct. So you correct your mistake. Like I always say, you know how to read error messages and correct it. So model. Now I've done my model. So this is my model, but I'm not interested in doing a regression analysis. I'm interested in two-way ANOVA. So the first thing I'm going to do is, let me test for homogeneity of variance. So I'm going to use the Levein test. This is what we did it in our last class. Let me show you. Levein test. So look at it. So Levein test of your model. So Levein. No, we have to call up a library. So let's call up a library. The Levein test is in the library car. So without calling up that library, you can't see it. So I can call it up now. Living test of your model 1. I can run it. The model must be saying the model must be completely cross formula only. See this. Model must be completely cross formula. A minute, please. Let me see. So it's telling us that model must be completely cross formula only. Okay, cross formula, that's supposed to be asterisk, not plus. Asterisk. Okay, correct. So it's for living test doesn't accept plus, accept asterisk. So this the living test is used to test for constant variance. Like I told you, we test for two assumptions, normality assumption and constant variance assumption. So what we are testing for now is the constant variance, also called homogeneity of variance, also called homoscedasticity. So that's what we are currently testing for. Homogeneity of variance or what? Constant variance or homoscedasticity. So looking at this, we are supposed to reject the null hypothesis that the variance is constant. Alternative hypothesis that the variance is not constant because the probability value is less than my level of significance, 0.05. So I'm supposed to reject the analysis. I will reject my analysis and say what. Now, when in a case where it doesn't satisfy the homogeneity of variance assumption, what will you do? You're not supposed to continue with this analysis. You look for another method that you use to test for the significant difference. Now, if you cannot get now, like I said, statistics will have parametric, non-parametric. The parametric, the power of the test of parametric methods or the test of non-parametric method. So most times we prefer using parametric method, but the parametric method has assumptions that must be satisfied. So whenever the assumptions are not satisfied, you can try to look for other parametric methods that you can still use to achieve the same result. Our result here is to compare the three companies and also compare the quality of bulbs produced by the three companies. So if we can get another parametric method we can use for this, awesome. But if we cannot get, we now look for the non-parametric equivalent of this method. So for now, let's look for a way to make this. So let me change the data set so that we can continue. I want to explain this, how to interpret this. So let me change the data set and see if it will satisfy the homogeneity of variance assumption. It didn't satisfy. So let me change again. It didn't satisfy. Let me change again. It also didn't satisfy. I want to explain this. Okay, awesome. So this has satisfied the assumption. So using this data set, the assumption has been satisfied. So what's the assumption? We are talking about homogeneity of variance assumption. So the homogeneity of variance assumption says that the variance of the error term must be what? Constant. So it has satisfied the assumption. Because it has satisfied the assumption, we can now continue with the analysis. Remember, I told you we're going to test for two assumptions. I didn't say we're going to test for only one. So the second one we're going to test for is the normality assumption. Normality assumption. So if it satisfies the normality assumption, then we can proceed with the analysis. So if it satisfies the normality assumption, we'll proceed with the analysis. A minute, please. Okay, let's continue, please. So let's test for the normality assumption. To test for normality assumption, we have to get our ANOVA two-way ANOVA model. So let me call it model 2. Model 2. So the code for ANOVA, which we did in our last class, AOV. AOV, then you write your model 1. AOV, then you copy this. You copy this. I wanted to use another method for this, but I think that will not be proper. I wanted us to start with the linear model, then use it to get our ANOVA, but I think it's not proper. So let's just go direct. So this is why we'll do our. Now, if I use my asterisks here, I'll be talking about two-way ANOVA with interaction. But that's not what I'm talking about now. Let me call this model 1. Let me run it. Let me show you what I mean. Let me explain what I mean by interaction now before I continue. Look at this. We only have companies and block. But if I change this to times and run, you will see the interaction. We have companies, block, then the combination, the effect of companies and block on the lifespan of the bulbs. In this case, we are not talking about the cumulative effect of both factors. We're only talking about companies. What's the significant difference between the 3 companies? What's the significant difference between the 3 quality of bulbs produced by the companies? Why in this case, we're talking about significant difference between companies, significant difference between the quality of bulbs. That's what we use to block it. Then also talking about the cumulative effect of companies and block. Is there significant difference between the cumulative effect of the companies and blocks? So that's what we are testing here. Like what we are doing now is two-way ANOVA, though with replication, but without interaction. So I will change this to plus. Correct. So you can't interpret analysis without testing for the second assumption. So we are testing for the second assumption, which is what? The normality assumption. So the code we are going to use for that, for the normality assumption. Now we can use 2 methods. We can use the graphical method. To use the graphical method, you do plot the model, the name of the model, which is model 1. That's what we call this, model 1, comma, then you put 2, comma, then put 2. So this is the normality plot. How do you interpret this? Now you say your data follows a normal distribution if all the points are on the diagonal line. If most of the points are on the diagonal line. It's possible that 1 may not be on the diagonal line, 2, few of the points may not be on the diagonal line. It's not a problem. But most of the points must be on the diagonal line. So looking at this, most of the points are on the diagonal line. So we can conclude that the data follows the errors of the data follows the errors of the model follows a normal distribution. We can conclude that the errors of the model follows a normal distribution. Now we have another way to test it. If you don't want to use the graphical method, you can use the Shapiro-Wilk test. Shapiro-Wilk test. Now, how do you use the Shapiro-Wilk test? First, you have to create a, let's say let me create a variable, let me call it model 2. Model 2 will be residual. Let me get the residual from the model, from the ANOVA model that we've done. Residual from the ANOVA model. So object, then you state the ANOVA model. What's the ANOVA model? Yeah, ANOVA model, we call it model 1. So I've been able to extract the residuals from the model. I've been talking about residuals. Okay, now let me explain what you mean by errors. If you write your two-way ANOVA model or one-way ANOVA model, you always end it with an error 10. Why will you end it with an error 10? You will discover that the model will not be 100% accurate. Estimates on the model sure will be close to, if your model is accurate, will be close to the actual values, but will not be 100% similar to the actual values. So when we're talking about the errors, we're talking about the difference between the actual value and the estimated value. Estimated means what the value you got it from your model. So if the actual value is 90, and after getting the parameters of the model told you that the value is 86, while the actual value is 90, you know that the error there is what, 4. So that's what we're talking about, the residual. So the errors there must follow a normal distribution, and the variance of the error must be constant before you can use two-way ANOVA analysis. So we are testing for the distribution of the error terms. So they must follow a normal distribution. So I'm using the second method, which I call Shapiro-Wilk. Let me spell it for you. Shapiro-Wilk. So we can Shapiro-Wilk test. So I said first you extract the residual. Residual is also called errors. Residual errors, the same thing. So we extract the errors from the model. So after extracting the errors from the model, I can now do my Shapiro-Wilk test. Shapiro-Wilk, Shapiro.test, that's the code, Shapiro.text. Then I will specify the error. So I've called the error what? Okay, let me change this thing from model to, let me not call it model, so let me call it residual. Or let me call it error. So I can type in error, yeah. Correct. Now, if you are using the Shapiro-Wilk test to test for normality, the null hypothesis is that the errors follow a normal distribution, while the alternative hypothesis is that the errors do not follow a normal distribution. So remember, you only reject when your p-value is less than 0.05. So looking at this, we are not going to reject. Why are we not going to reject? The p-value is greater than 0.05. So it means we are going with the null hypothesis that says that the errors follow a normal distribution. Now we have used two methods to confirm that the errors follow a normal distribution using the plots. We call this the normal probability plot. Normal probability plot. So we use the normal probability. Okay, this is the norm. I think it's the quantile plot. Normal quantile. I don't think it's the probability plot. But so we use this NQQ plot. We have MPP plot, which is normal probability plot. So what I got here from R is normal NQQ plot. Let me check something. Plot. Let me change this number to 3 and see. 3 is scale. Let me change to 4. 5. 1. Okay. So you gave us NQQ plot. Normal. So look at the quantile plot. It's also used to test for normality. So for you to say the errors follow a normal distribution, the point must be on diagonal line, most of the points. Also, you can use the Shapiro-Wilk test, which we've done. For the Shapiro-Wilk test, your p-value must be greater than 0.05. Why? Because the null hypothesis is that the errors are normally distributed, and the alternative hypothesis is that the errors are not normally distributed. So if you reject your null hypothesis, that means you can't continue with the analysis. You have to look for another method that will be suitable for your work. So since my data are satisfied all the assumptions, I can continue with my analysis. That means I have to bring my model again. I'll bring it down. I'll bring it here. So I can write my comment. The data have satisfied or have satisfied my assumptions. So I can run my ANOVA now. So this is how to write your ANOVA. These are the two factors. Remember, we are talking about without interaction. So that's why I think this is plus without interaction. I've told you how to interpret this. So we use the p-value to interpret. The null hypothesis is that there is no significant difference in the three companies. There is no significant difference in the three companies. Why the alternative hypothesis is that there is a significant difference in the three companies. Looking at this, are we rejecting the null hypothesis or not? Yes, we are rejecting. Why are we rejecting? Because the p-value is less than 0.05. Since the p-value is less than 0.05, we reject and we conclude that there is a significant difference in the lifespan of bulbs produced by the three companies. There is significant difference in the lifespan of bulbs produced by three companies. Then we'll move over to block. Looking at the block, is there a significant difference? That means we're trying to test if there's significant difference in the quality of bulbs. That means we are looking at and is there significant difference between the lifespan of energy bulbs? Is there significant difference between the lifespan of cheap bulbs? Is there significant difference between the lifespan of expensive bulbs? So that's what we are testing. Looking at this, is telling us there is no significant difference. That means the lifespan of the three bulbs is the same. If I do this analysis and I make this known to the public and tell them that the lifespan of the three bulbs are the same, I don't see, most people may discover that there is no need going for the expensive bulbs if the expensive bulbs will spoil the same time as the cheap bulbs, except the quality are different. But talking about lifespan, they are all similar, they're all the same. That's what our analysis is telling us. That the three bulbs, the energy bulbs, cheap bulbs, expensive bulbs, they all have similar lifespan. So there's no significant difference. How did I know? Because the p-value is greater than 0.05. Now, you see, I'm not typing the interpretation. Like I said in our last class, I'm not going to type any interpretation again. I mean, that's what I said in our last class. Why? Because I've done that already. So just go back to what we did in our last class, and all I've said now, just type it. So first, if I want to do this analysis, they give me a work to do two-way ANOVA. First, I will tell them that I'm going to do a two-way ANOVA. Then I will tell them the reason why I'm doing a two-way ANOVA will have two factors. So that's why I'm doing a two-way ANOVA. And I will state that for me to do the two-way ANOVA, I have to test for the assumptions. And I will state the assumptions we have. So we have, for two-way ANOVA, we have the normality assumption, we have the constant variance assumption, also called homoscedasticity, also called homogeneity of variance. Homoscedasticity, the spelling is HOMOSCEDASTICITY, homoscedasticity. So we have constant variance and we have homogeneity of variance. So I tested for that using the Levene test. Then you also copy your result and paste. Then you talk about the normality assumption. You tested using, you can use, you must not use the two plot, the normal QQ plot and Shapiro-Wilk test. You can decide to use only one. If you want to use the two, your choice. You are free to do what you want. So then you write, then we are going to test for the second assumption of the normality of the error term. With the other hypothesis that the errors follow a normal distribution, while the alternative hypothesis is that the errors do not follow a normal distribution. If you are using the Shapiro-Wilk test, that means you need your alpha. Then we are going to use alpha of 0.05. Then you copy your Shapiro-Wilk test results, which is this. You copy and paste it and make your decision rule. We are going to reject the null hypothesis if the p-value is greater than 0.05. And from our result, the p-value is greater than 0.05. We are going to reject if the p-value is less than 0.05. And from our result, the p-value is greater than 0.05, which means that we are not going to reject our null hypothesis. So we are going to conclude that the errors follow a normal distribution. So you continue. Since the data have satisfied all the assumptions, we can now proceed with the two-way ANOVA. Then you state the null hypothesis. The null hypothesis for the two-way ANOVA is that for two-way ANOVA, remember we are testing for three things. First, for two things, we are testing for the significant difference for companies and significant difference for blocks. So you can make a sub-heading. After you've tested, you put two-way ANOVA. So you put a sub-heading, significant different test for companies. Then you state your null hypothesis. There is no significant difference between the three companies. Alternative hypothesis, there's a significant difference between the three companies. You state your level of significance. You copy your table, your results here. You copy the results here, or the result should have been copied. Then you make your decision that we are rejecting the null hypothesis and we are concluding that there's a significant difference between the three companies because the p-value is less than 0.05. Then maybe you can put a sub-heading, significant difference for block. Your null hypothesis that there is no significant difference between the three quality of bulbs produced by the companies. The alternative hypothesis is that there is a significant difference between the three quality of bulbs produced by the three companies. Quality of bulbs here will mean energy, cheap, and expensive. Then you state your level of significance 0.05, or you can decide to just state level of significance once, maybe at the beginning, that all the tests that will be done here, the 0.05 level of significance will be used. You can just state it once from the beginning and tell them that you're going to use it for all the tests and try not to repeat it again. or you can decide to keep on repeating it. So you make your decision. So we are not going to reject the null hypothesis for block because the p-value is greater than 0.05, which means that the lifespan for the three quality of bulbs are similar. That's all. We have done a two-way ANOVA design. Very simple. Now, how do you do two-way ANOVA with interaction? The only difference, if you're talking about with interaction, the only difference is to change this plus. Look at the screen. Change this plus to auxiliary times. When you change it to times, that's all. Just run the same thing. Look at the result. They're almost similar, but they are different. So in this case, now we have the interaction effect of companies and block. The interaction effect is also not significant, meaning if both of them, the cumulative effect of both of them on the lifespan is not significant. Block, only the quality of block bulbs is not significant, but companies, they are significant. So that's the meaning of this. So I've taught you two-way ANOVA with interaction and two-way ANOVA without interaction. I've also explained how to test for the assumptions. So I think that's very simple. So the next thing we're going to treat now is linear regression. Then after linear regression, we can talk about chi-square test.